いいですかね。はい。Good afternoon. I am Hiroshi Shigenobu from Kitami Institute of Technology. Today, I present a novel neuro-symbolic approach to irony detection based on structural components of ironic statements. Here is the outline of my presentation. First, let me introduce the background. Online communication has brought serious issues like cyberbullying. As shown in the graph, reported cases in Japan have increased steadily, exceeding 20,000 in 2021. Therefore, automatic detection of harmful content has been actively studied. For example, happy birthday is positive, and he is stupid is negative. However, a phrase like, wow, you are a genius, can convey negative sarcasm depending on the context. In this way, irony involves a mismatch between surface expressions and true intent, which makes automatic detection a challenging task. In a previous study by Dan in 2023, a dataset of Japanese tweets was constructed. They defined irony as an utterance with an evaluated expression opposite to the genuine intent, and annotated 5,400 tweets on a 5-level scale. However, re-annotation revealed a major difficulty. As shown in the red box, 56% of the tweets collected as ironic candidates were labeled as ambiguous or uncertain. This shows that even for humans, identifying irony with that clear context is extremely hard. On the other hand, non-ironic sentences were much easier to identify, with the vast majority consistently labeled as not ironic. This asymmetry suggests that we need a better way to capture the distinct features of irony. Let's look at some examples. The third one, Arihara that's just so like you, is rather ambiguous. Without knowing the context, such as the game result, we cannot tell if this is praise or sarcasm. However, structurally, this sentence contains specific components. An intensifier, more, a praising expression, さすが, and a casual ending, だわ. Depending on the game result and Arihara's reputation, this sentence can be either genuine praise effectively than just looking at the whole sentences. Our hypothesis is that by analyzing these structural components, we can detect irony more effectively than just looking at the whole sentence. This leads to our research objective. Our goal is to improve irony classification beyond conventional transformer-based baselines. Transformers are accurate but act as black boxes. We propose a method that extracts structural features of irony. This approach aims to classify sentences with limited data while providing a clear, interpretable rationale for the decision. Here is the overview of our neuro-symbolic method. First, we defined ironic components. Then a neural model extracts these components like mode, obj, pose, etc. Finally, a symbolic model classifies the sentence based only on this sequence of tags. This approach combines the best of both worlds, the high accuracy of neural AI for extracting features and the explainability of symbolic AI for making the final decision. Now, I will explain the previous study used as our baseline. We use the re-annotated dataset of 5,400 tweets. We created a balanced binary dataset of ironic and not ironic tweets with 1,111 for training and 124 for testing in each class. As a baseline, we used fine-tuned transformer models. The best performing model was Roberta, achieving a macro F1 score of 0.755. Our goal is to surpass this score. Now, I will explain our neuro-symbolic method in detail. The first stage is the extraction of irony components. Based on the definition of irony, we consider three core elements: the target of irony, the evaluative expression, and the speaker's true intention, which is the opposite of the literal evaluation. These ideas guide the design of our labels. We finally define 6 tags: obj for the object for tag of irony, pos and neg for positive and negative evaluations, mod for intensifiers and other modifiers, H and F for honorific or polite forms, and COL for colloquial or slang-like expressions. The last 3 capture stylistic cues that often strengthen the ironic tone. For the extraction experiment, we used 2,200 sentences. We fine-tuned language models to perform token classification, assigning these tags to each word in the sentence. We compared several pre-trained models, including BART, Rzepka, and Roberta, which showed good performance in previous studies. For evaluation, we used the SQL library to measure precision, recall, and F1 score based on tag spans. Here are the results. The best model for irony element tagging is Roberta, which achieves an F1 score of 0.616. Overall, F1 scores are around 0.6, mainly because the spans of positive and negative expressions are often wrong and ambiguous. This slide shows some examples of tagging results produced by the best model. With these moderate scores, the model still captures many key components correctly, which is sufficient for our next step. In the sentence level classifier, we only use the sequence of tags, so small span errors have a limited impact after abstraction. The second stage is irony classification. We abstract the sentence into a tag sequence like neg, obj, pos, etc. Our objective is to classify irony based on these sequences and surpass the baseline F1 score of 0.755. The overall pipeline is as follows. The sentence is converted to tags. We extract features like n-grams from the tags. And finally, a classifier predicts irony or non-irony. We use the same dataset as the baseline. Note that for the test set, we use manual annotation to ensure reliability. There were 90 sentences where no tags were detected. We compare 3 systems. The baseline is Roberta trained on raw text. The proposed method uses only tag sequences and treats the 19 untagged test items as incorrect, achieving 92% coverage. The hybrid method classifies those 90 items with the baseline and combines both outputs. Our experiments proceed in two steps. First, we perform pattern analysis on the 1949 training sequences and identify n-grams and skip-grams of tags that contribute to irony. Second, we convert these patterns into TF-IDF vectors and test various classifiers to see how well tag-only features can distinguish irony. Here is the result of the pattern analysis. The bigram neg pose has a high coefficient for irony. This empirically proves the crash of sentiment theory. Also, core HNF is a strong indicator showing that mixing politeness with slang is a common ironic technique in Japanese. For the classifier, we tested various algorithms. Our boost classifier achieved the best F1 score of 0.77 using these tag features. Therefore, we chose it as the main classifier to refine further. We further optimized our boost. We find that using simple unigrams and bigrams worked best. F1 0.78. Skip grams increased dimensionality too much and reduced performance. So we use this optimized boost model for the proposed and hybrid methods. The hybrid method covers the 19 no-tag instances using the baseline. Here are the final results. The baseline achieved 0.739. Our hybrid method achieved 0.783, improving the macro F1 by amount 0.04. Although the p-value is 0.267 due to the small test size, we achieved higher accuracy while providing better interpretability. Finally, I will summarize my talk. We propose a neuro-symbolic approach that models irony based on structural components. By converting sentences into tag sequences, we made the decision process transparent and interpretable. Our hybrid model exceeded the strong Roberta baseline. Future work includes data augmentation to improve statistical significance and handling sentences with no explicit tags. Thank you very much for your kind attention.